All right. So, hello everyone. Welcome back to the PC seminar. And we have with us today Professor Ignasi Sau from LIRMM, University of Montpellier, CNRS, France. And he'll be speaking on kernelization of maximum minimal vertex cover. So thank you so much for joining us. Over to you now.
Okay, thank you for the invitation. So I will speak about what the title says. It's a joint work with Julio and Victor from Fortaleza in Brazil and Maran Bougeret from the LIRMM, who I see also now in the audience. So hello, Maran. For if anyone is interested in this work and you want to go to see the archive version, better wait a couple of weeks because we plan to upload a new version by 2 weeks, let's say. Okay. So I will speak about why we study this problem. I will describe the results we have, and depending on time, I will sketch some of the proofs, and I will state some open questions in which you may be interested. So why one wants to study the maximum version of a problem? So assume you have a problem in a graph and you want to minimize the size of a vertex set, like a dominating set. Then let's say the most naive heuristic will be like, okay, start with the whole graph and start removing vertices greedily until your set is not a dominating set anymore. Then the maximum minimal version of this problem corresponds to the worst case that can happen when applying this strategy. So in this sense, it is natural to try to see how bad can it go. So this paradigm has been applied to several problems. Maybe the most known one is the maximum minimal dominating set, that it has even a name. It's called upper domination. But this approach has been also applied to heating set or to feedback vertex. Okay. So in this talk, I will apply to the vertex cover problem. So I will focus on the following problem, which I will abbreviate as MMVC. So I'm given a graph and an integer k, and the question is if my graph contains a vertex cover that is minimal and that size is k. Okay, so I guess everyone here in the audience now, a vertex cover is a vertex subset that contains at least one endpoint of every edge. Okay? So in this case, the problem is not only interesting because of this motivation about it, because it's like the dual problem also of a widely studied one, that is the minimum independent dominating set. So I claim that the complement of a minimal vertex cover is an independent dominating set. And why is that? Well, suppose here in the picture that X is a minimal vertex cover. So its complement by definition needs to be an independent set. And since X is minimal, it means that every vertex here in X has at least one vertex outside. Otherwise, it will be removed from the vertex cover. So in other words, if I look at it from the outside, it means that for every vertex here has a neighbor. For every vertex not in this set has a neighbor here. So this set is an independent dominating set. So maximizing these sides is the same as minimizing these sides. So these problems are dual in this sense. This is an easy observation that I will use in what follows. So we have the following easy fact. So I claim that a vertex set of a graph is a minimal vertex cover, even only if it is a vertex cover. And additionally, for every vertex in the set, its neighborhood, it's not completely contained in the set. I mean, it's very easy. So suppose here that I have a set X, and I want it to be a minimal vertex cover, but assume that I have a vertex here, the red one, such that its whole neighborhood is contained in the set. Well, then it's not minimal because I could remove this guy, put it outside, and all its incident edges will still be covered. Okay, so this will not be minimal. So this easy characterization is useful when analyzing some of the properties of this problem. So let's move on. What was known about this problem? I mean, even if it's quite natural, let's say, I mean, surprisingly, at least to me, there is not that much previous work. So let me just list it. And if I forget some, please interrupt me. So Fernau, in his habilitation in 2005, studied this problem and provided some FPGA algorithm under several parameterizations and gave several remarks. We'll come back to this habilitation in a few slides. Then there was this article that provided a very nice set of results by Bodia de la Croce and Pascos. In particular, they provided FPT algorithms for a variety of parameters. And they show that the problem can be approximated within square root n, which is quite poor, let's say. But one cannot do better. They also showed that this is best possible. So an approximation algorithm with a ratio better than n to the 1/2 doesn't exist unless p equal to p. Then Sehavi provided FPT algorithms even for the weighted versions, parameterized by the size of a vertex cover and prove its optimality. And there is also a couple of recent articles that deal with the inapproximability of this problem in some exponential time. Okay. So I haven't mentioned kernelization in purpose, so let's speak about it. So what is known about the kernelization of this problem? So let's first start with a simple remark. So here, just recall, I'm given a graph G, integer K. I want to know whether my graph contains a minimal vertex cover of size at least K. Okay. So suppose that my graph contains a vertex that has degree at least K. Okay. So for instance, here in the picture, suppose that K equals 4, and I have this vertex V here that has degree 4. Then what can I do? I can start growing a minimal vertex cover as follows. So here I'm growing it with the red vertices. So I don't put V in the set. I put all its neighbors in the set, and then I complete it any way I want outside until I make it a vertex cover. Okay?
Excuse me,
then,
I would like to ask a question.
Yes, please.
So regarding the kernelization, so what is your parameter here? Is your parameter the size of the maximum minimal vertex cover, the size K, at least K, that K?
Yeah, that K, yes. It's true that I didn't precise this. So yeah, the parameter is the natural solution, the natural parameter. So the solution size is the size of the set I'm looking for. Okay.
Okay.
I will speak about another parameterization in a few slides.
Yes, so that was the size of a minimal vertex cover of the graph. That was what Merab-Zehavi's work in 2017 was about. Now,
yeah, this was another parameterization.
Yes, for your case, it is the size of the solution.
Exactly. In this slide, yes.
Okay.
Exactly. Okay. So here parameterizing by the solution size. So what I was saying is, let's start with an open neighborhood of V, and then let's say complete it in any way until a minimal vertex cover is found. And then since V is not in the set, none of these vertices will be removed when making it minimal. Okay, so the solution that I will obtain will at least have size the open neighborhood of V. Okay, so I have a yes instance. Just trivial. So I may assume that my graph has maximum degree at most K-1, and then I can make an analysis similar to the high degree rule for vertex cover. Since I have maximum degree at most K-1, if I have a vertex cover X on my graph, vertex cover, I don't need it to be minimal. I can cover at most X times K-1 edges by the degree condition. So assuming that I remove isolated vertices that can be done safely, it follows that my vertex, the vertex set of my graph has size at most X times K. Okay? So if I can just take my graph, remove isolated vertices, and look at the vertex size. If I have at least K square vertices, I know that any minimal vertex cover will have size at least K. So I can answer yes. Okay. So this leaves a trivial, this yields a very easy kernel of quadratic size. Okay. So the natural question is, can we do better? Okay. As you all know, for vertex cover, a very similar approach works, just replacing yes by no. And the question is, can we do better? Okay, let me present here a strategy that was proposed by Fernand in his habilitation to obtain a linear kernel, again with the same parameter, the solutions. Fernand proposed the following. So given an instance, a graph in a parameter K, like the one in the picture, let's consider any spanning tree of G. Okay? And let's root it an arbitrary vertex. So here I assume that the root in my picture is the leftmost vertex. Then what we can do is we partition the vertices of this spanning tree according to the parity of the distance from the root in the spanning tree. Okay? So the set V0 contains the vertices that are within even distance from the root, and similarly the set V1 contains those that are at odd distance from the root in the spanning tree. Okay, so then take the set that has the largest size. So assume that, for instance, here the red one, V0, has the largest size. And then our goal is to obtain a minimal vertex cover that contains this whole set. So what do we do? I start, again, here the red vertices to me are those that will be contained in the minimal vertex cover. So I start with a candidate containing all these red guys. This is a good start. Why? Because by construction, each of these red guys here has at least one black neighbor. Okay, so this is good. This is good news for the minimality condition, but it may still not be a vertex cover. I mean, why? Because I may have an edge that is fully contained in a blue part. Okay, so then what we can do is we complete it greedily, let's say. We keep these guys and we add vertices until we do have a vertex cover of the whole graph. Okay. Then what can we say? Well, I have built a vertex cover and it contains the whole set V0, and since the size of the set is at least V0, so I can conclude if my graph has size more than 2k, then at least one of these two sets has size at least k. So I will always obtain a vertex cover of size at least k, and that is minimal. So I can assume that my graph has a size at most 2k. Okay, this would be very nice. The problem is that it doesn't work. Why? Because when I have greedily added these red guys in the blue parts in my set, then maybe I have lost the minimality condition in the guys that were originally in the red sets. For instance, now this guy here, it has its whole neighborhood contained in the candidate for the minimal vertex cover. So by the easy property that we saw, this guy cannot be part of a minimal vertex cover. So I need to remove it. And in fact, we can find examples where the number of vertices that need to be removed can be arbitrarily large. So I cannot guarantee that I can, with this strategy, I can find a vertex cover always of size at least half. So it doesn't work. Okay? So if the strategy doesn't work, unfortunately, well, or fortunately, because this was our starting point for this work. So in fact, the set of authors remarked, maybe it was known before, that given a set of vertices, deciding whether the set can be extended to a minimal vertex cover, this is an NP-hard problem. So making this extension procedure is hard, so it cannot be done in a kernelization algorithm. So then in this article that I told you about in 2015, these guys asked explicitly for the existence of a subquadratic kernel with this parameterization. Okay, so what do we prove? Now I switch the parameterization only in these slides and in the proof. So the first question that we ask ourselves is, okay, we have seen that with taking as the parameter the solution size, I can very easily obtain a polynomial kernel. The question is, what happens if I take parameters that are maybe smaller than the solution size? Does the problem still admit polynomial kernels? And the most natural parameter in this direction is the size of a minimum vertex cover, because this will always a lower bound on the size of a minimal vertex cover. And what we prove, our first result is under the standard complexity assumption, it is not possible. I mean, this problem does not admit a polynomial kernels with this parameter, even on bipartites. Okay? So this complements the results that were presented in previous algorithms about FPT algorithms with this parameterization. And of course, as a corollary, also this rules out FPT algorithms by tree-width because it's smaller than the vertex cover number +1. So this is our first result. Now let's go back. Let's come back to the solution size k as the parameter, okay? And let's go back to the question I told you. So can we obtain subquadratic kernels for this parameter? And what we do here to partially answer this question is to introduce a new framework to provide lower bounds on kernelization, and that I will discuss in a while. So this framework applies not only to this problem, to MMVC, but to any vertex maximization problem. Okay, so I will present the ideas for any vertex maximization problem pi that is parameterized by the solution size. Okay. So we have a parallel definition for vertex minimization problems as well that will appear in the new archive version of the article, but I will not discuss it here. Here in this talk, I will just focus on the vertex maximization version. Okay, so to define it, let me just recall what is a kernel, because I will show you what is the difference with the classical definition of a kernel. So here is the typical definition of a kernel from a parameterized. Okay. So it's a polytime algorithm such that if I'm given an instance gk, I obtain an instance g prime k prime, such that its size is bounded by some function of the original parameter, and this function is called the size of the kernel. And so that these instances are equivalent. So let me write it in the form of two items because I will need it before. So these two implications, of course, imply that these two instances are equivalent. Since I'm restricting myself to vertex maximization problems, I can rewrite these two implications as follows. I can just say this is exactly the same as G prime K prime being a yes instance. So if the optimum of this problem in G prime is at least K, then the optimum of this problem in G is at least K. So far I have just rewritten the definition of yes instance. So now let's see with what is the type of kernels that we use. So in fact, we introduced a type of kernel that is a restricted version of the general definition, and we call it a large optimal preserving kernels. Okay, that I will abbreviate as LOP kernels. So LOP stands for large optimal preserving kernels. Okay, so what is the difference with respect to a general kernel? The difference is the following: the first 4 lines are exactly the same. The only difference is in the second implication. Okay, the second implication changes as follows: if GK is a yes instance, if the optimum in G is at least K, then I'm not asking only that the optimum of G prime is at least K prime. I'm asking that the optimum of J prime is at least the optimum of that I had in G minus the drop in the parameter that I have done. Okay, so assume that K prime is at most K for simplicity. So why this is stronger? Well, since I'm in this implication, I have that optimum. The optimum of G is at least K. So this is at least 0. So this implies that the optimum of G prime is at least K prime. Okay. So asking for this implication implies the original implication that I need for a typical kernel. So this is a stronger version of a kernel. Okay. So it's a restricted type of kernel. Okay. So this is what we call a LOP kernel. And in general, if we have an instance and I have a reduction rule that satisfies these two properties, I call such a reduction rule a LOP rule. Okay? And then a LOP kernel can be defined as a kernel that is obtained by using only LOP rules. We can give ourselves a little more freedom, and our framework still applies. So we can also allow the kernel to just answer yes. So as you know, typical kernels, we simplify, let's say, the formalism sometimes by saying, okay, this is a yes instance and this concludes the kernel, okay, instead of outputting a trivial, let's say, constant size instance. So in this case, outputting a trivial constant size instance may not satisfy the second condition, but still we allow it. Okay. So a LOP kernel for us, a LOP kernel, the way we define it is a kernel that satisfies this property or that answers yes. Okay. So this is a LOP. So of course, these LOP rules look like particular reduction rules. Okay, because I am asking for a stronger implication. So I will show you an example of a rule that is not a LOP rule for the MMVC problem. So assume I have an instance, GK, and assume that in this instance, I have a vertex here that has strictly more than K, let's say, pendant neighbors. So of course, this is a yes instance, but I will not answer that this is a yes instance. I will apply the following reduction rule. I will just keep the same parameter K, and G prime is just obtained from G by cutting off all the neighbors of V except for K of them. I keep K of them. So still, this is a yes instance. So this is a valid reduction rule. And why it is not a LOP rule? Well, what I want for it to be a LOP rule is that if the MMVC, by MMVC, I mean the size of a maximum minimum vertex of G is at least K, then this is what I want for it to be a LOP rule. And in this case, since K hasn't changed, this is exactly MMVC of G. But this inequality may not hold because when going from left to right, I may have destroyed the optimal solution. Maybe this guy had 1,000 pendant neighbors, so I may have a MMVC of size at 1,000, and here I have just kept 10 of them if K equal 10. Okay, so I may have dropped the optimum arbitrarily. So this reduction rule is not a LOP rule. But as I say, I could very well have answered yes. So in this case, I mean, this pathological example could be easily circumvented by just answering yes. So in fact, I mean, here I ask you to believe me because I have not defined log rules for minimization versions problems. But let's say, just keep in mind that there are rules that do not destroy the optimum arbitrarily. Let's say, so it's easy to verify that the typical rules for vertex coverage, such as the high degree rule or even cloud decomposition or name-house cluster, are log rules. And in fact, more involved rules are those based in production replacement or in metroids as also log rules. So in fact, we don't know of any rule for, let's say, any natural rule that has been really applied to an existing problem that is not a rule. So we do think that this is a restriction, but we haven't been able to find explicitly a rule that is not a log rule. So maybe you can help us in this direction. Okay, so what do we prove using this restricted version of kernel? So what we prove is that if we have a log kernel of certain size, I mean, here is all about the degree of polynomial kernels. Okay, it's not about ruling out polynomial kernel. It's about optimizing the degree. So what we prove is the following: that a log kernel of a certain size implies an approximation algorithm. So more formally, if pi is a vertex maximization problem where r and epsilons are numbers in the interval 0, 1, then if this problem admits a log kernel with so many vertices, then it admits a polynomial time approximation algorithm with this ratio for some extremely positive constant epsilon prime. Okay, so how can it be used? Then, if I know that this problem does not admit some approximation ratio, by reversing the implication, I can deduce that it does not admit a log kernel of certain size. So, and we have a similar statement for vertex minimization problems. So how can we use it? Well, first, let me just very briefly make an overview, probably incomplete, of other existing techniques to rule out polynomial kernels. So this is to obtain kernel lower bounds. So we have the framework of compositions that is used to rule out polynomial kernels. So this is not what we are interested about. So let's say our competitor, which is of course much more powerful, is the framework of weak compositions that can be very successfully applied to give lower bounds on the degree of polynomial kernels under this assumption. And then we have other like polynomial parameter transformations that are very, very handy to, once I know that some problem does not admit a kernel of certain size, I can transfer this hardness to another problem. Then I have other techniques that are used to give lower bounds on the coefficients, on the constants, typically of linear kernels. So this is not what we are interested about. And then we have the framework of lossy kernelization. I mean, this is not strictly, I mean, this is not a framework to give lower bounds. I have put it here because in this framework, there is a relation, there is implications between the approximability of certain problems and the existence of certain kernels. Okay? But this is inherently different in the sense that here is a two-way reduction. The kernel needs to produce a solution and come back to the original. And we have, as far as we have verified it, our framework is uncomparable to this. So my message here is that our framework, while not being probably as applicable as the previous ones, can be seen as an additional technique to obtain kernel lower bound. So the strong points of what we propose, in my opinion, are that it's very easy to apply because we just have to take an approximability result and it immediately gives a lower bound on the kernel. And also it has the advantage that the hypothesis is just that P is different from B, which is weaker than the standard hypothesis in kernelization lower bounds. But also, I mean, I will not say it's the panacea. I mean, it has also weak points. Probably the weakest point it has is that for it to be applicable, it needs to the problem in which we want to apply, it needs to have a very strong inapproximability result. It needs to have an inapproximability of the form n to the some constant. And it only applies to vertex problems, but this, in my opinion, is not as bad. Okay, so how can we apply it? So this is in this box, the summary of our results. So how can we apply it to the MMVC problem? Well, as I told you, Boria and others first proved that NDC cannot be approximated better than n to the 1/2. So I can just put R equal to 1/2 in this implication, and I immediately have that if I put 1/2 here, is 1 minus 1/2 is 2. I mean, it's 1/2, and it goes up in the numerator. So I immediately have, as a corollary, that maximum minimal vertex cover parameterized by the solution size does not admit a log kernels with a strictly less than k-squared vertices. Okay, so this means that the trivial kernel that I presented to you is essentially optimal. I mean, just a remark here. This result here does not imply that I cannot obtain a kernel of size less than k-squared. What it means is that if it exists, it needs to do something really different from what is known for vertex cover, at least, or it needs to use reduction rules that are somehow like non-standard for a reasonable definition of a standard. And let me mention to you another consequence of this result that we obtained. Here I'm switching the problem. So Dubois and others recently studied the max-min version of feedback vertex set that is defined in the natural way. And among other results, they proved that the problem, again, with the solution size k as the parameter, admits a cubic kernel. And they asked whether there's a kernel that has a smaller size. And they also proved that there is an approximation, I mean, that the problem cannot be approximated better than n to the 2/3. So it really looks like a candidate for plugging it into our framework. And we're very happy to realize that if we just plug R to the 2/3 here, 1 minus 2/3 is 1/3, so the 3 goes up. So we immediately have that this problem cannot, it does not admit a log kernel of strictly less than k-cube vertices. So we were really happy when we realized it. And I mean, it cannot be just chance, right? I mean, they had this 2/3, they have the k-third, and it just matches perfectly. So we think that we have found some nice implication between the degree of the kernels and the size of the best existing approximation algorithms. So we were happy that it has also these consequences for the feedback vertex set. Okay, so now that we more or less rule out subquadratic kernels, our last goal was, okay, is there any interesting case in which still we can obtain subquadratic kernels? And for this, we used, again, to the best of our knowledge, the first time the ergo-signal property in kernelization. So I will define it later. Don't worry if you don't know it. So what we proved, for instance, is this kind of results, that the problem, if we restrict it to Wolfrey graphs, then I can obtain a polynomial kernel, namely if I restrict to some class of graphs. Here by Wolfrey, I mean, can you hear me well? Because I get a message here that my connection is unstable. So if you can.
Yeah, your audio was gone for a few seconds, but it's back now.
Okay, okay. Connection is supposed to be good. I don't know what happened. So here, when I say Wolfrey, I mean as an induced subgraph. Okay. So, well, know that the problem is NP hard here because, for instance, the problem is known to be NP hard on bipartite graphs that are, of course, Wolfrey. So the problem is NP hard, but still it admits a quadratic kernel. And we proved several similar properties for other graphs. I will not list them all here. Here, the important was more the technique and the idea that the classes themselves. For instance, in KT graphs, KT3 graphs, we proved we gave this exponent, which is strictly smaller than 2. And for POFI graphs, we achieved an exponent 5/4, where the PO is a triangle plus a pendant edge. Okay, so in the next 20 minutes, say, I will just give some ideas of the proofs. So let's start with the first result I told you about, is the lower bound. The one that says that if I take the size of a minimum vertex cover as a parameter, I cannot obtain a polynomial curve. And what we do here is we use a polynomial parameter transformation. So let me recall it briefly. A PPT is an algorithm that works in polynomial time and transforms an instance of a problem to an instance of another one while preserving equivalence, and such that the parameter of the target problem depends polynomially on the parameter of the source problem. So if here is the application is simple. If this problem does not admit a polykernel under some assumption, like for instance the standard one, and I can reduce, like I can find a PPT to a target problem, then the target problem does not admit a polykernel as well. So we apply this technique by reducing from the monotone subproblem, taking as the parameters the number of variables in the form, which is known not to admit a polykernel. So in the monotone sat problem, I have clauses. I don't restrict them to have size 3. And within each clause, the variables are either all positive or all negative. Okay. So of course, if they were all positive in all clauses or all negative in all clauses, this will be trivial. So I have positive and negative clauses. But within each clause, either all positive or all negative. So the reduction is simple. Let me sketch it. So given a formula, given an instance phi of the monotone set problems, assuming it has n variables and n clauses, I do the following construction. I do this. So for every variable xi, I add a p4, in which one identify one vertex with a positive literal corresponding to the variable and one with the negative literal of the variable, and I do it n times. Okay, and then I put one vertex per clause, and just for every clause, I just link it to the literals it contains. Okay. So since I'm dealing with a monotone version of SAT, then I have two types of clauses, positive ones and negative ones. So in the positive ones, they only see the xi plus, and in the negative ones, they only see the xi minus. So this graph is bipartite, okay, because of this bipartition. So this is good because we wanted also to obtain a Harnett result in bipartite graphs. And I set my solution size to be 2n plus n. What does it mean? I mean that here I want to take in the solution two guys in every P4 and all the closed vertices. So let's see why it works. First observation also is that for it to be a PPT, I need that the parameter is preserved polynomially. So note that if I take the two endpoints of the central edges for each of these n P4s, I obtain a vertex cover of this graph because I'm left with an isolated set of vertices. So the size of a minimum vertex cover is 2n here, which is linearly depending on the number of variables. So I'm indeed preserving the parameter, so this is fine. And now let's verify quickly that I have equivalence. We claim that the formula is satisfiable even only if this graph here contains a minimal vertex cover of size k. So let's start with the easy direction, but the ideas are very similar. So suppose that the formula is satisfiable. So I claim that this red set is a minimal vertex cover. How is it constructed? I first put all the variable vertices in the set, all the closed vertices in the set, and then for every variable, I put in the set the literal that does not correspond to the true assignment. Okay, so I put in the set the false assignment of every literal, and then if I choose this guy, for instance, then I put in the set the non-adjacent guy in the P4, and similarly, if I put this guy in the set, then I put the non-adjacent guy in the set. Okay, why is it, well, is it easy to verify that it is a vertex cover by construction? Why it is minimal? Well, the minimality within the P4s is fine because for every vertex in the set, I have one neighbor outside, so this is good. Now let's look at the closed vertices. Well, and since the formula is satisfiable, for every closed vertex, I have at least one guy that corresponds to a true assignment. But since I have chosen the false assignment, then I have for every clause, I have at least one guy that is not in the red set. So for every clause, I have at least one neighbor that is not in the minimal vertex cover. So it's fine. I cannot remove this guy from the set, and this applies for both positive and negative clauses. And the reverse direction is very similar. So suppose I have a set of this size, then look at the P4s. No P4 can contain 3 or more vertices in a minimal vertex cover, because in this case, I will have 2 consecutive red guys. And this guy here that has degree 1 will have its whole neighborhood in the set, so it will not be minimal. So I have 2 guys here, and then the analysis is the same. I need to contain all the closed vertices, and for it to be minimal for every clause, I need at least one guy that is not in the set. So then I take the assignment in this variable to be the corresponding yes or no. So this is a simple reduction. Let's move to the ideas behind our new framework. You will see that it's very simple. I will skip some details, but the idea is really simple. So we were quite happy when we realized it. So here is just, I'm recalling the definition of a lob kernel. So recall that this is the extra condition, that I'm asking the optimal not to drop. Okay, so I want large optimals to be preserved when moving from G to G prime. And I also allow my kernel to answer yes. Okay? And this is the kind of statement, this is the statement that you want to prove, that if I have a kernel of a certain size, then I can obtain an approximation algorithm with a certain ratio. What is the idea? So take a general vertex maximization problem, parameterized by the solution size. And suppose that pi admits a lob kernel of size k to the c for some c. Then, okay, given an instance, we apply this kernel on it. So the output of this kernel can be either a yes answer, so a certificate that the optimum of G is at least k, or it produces an instance G prime K prime such that the stronger property is satisfied. Okay, so here I have reversed the inequality. So I have a certificate that the optimum of G prime is large. So I look it from the other side. I know that in case an equivalent instance is produced, the optimum of G is bounded by the optimum of G prime plus the drop in the parameter. But now I just used that the optimum of G prime, since it's a vertex maximization problem, is at most the size of G prime. I've used that K prime is at least 0. So this is at most the size of G prime plus K. And here I just use the fact that the kernel has size K to the C. So this is at most O of K to the C. Okay. So in polynomial time, what I have done, in polynomial time, given an instance, I have either a certificate that the optimum is at least K, or a certificate that the optimum is at most K to the C. Okay, so I have this has really the flavor of an approximation algorithm. In poly time, I have a certificate of large optimum or small optimum, but with a gap. Okay, so here with the standard techniques, I just cooking up the numbers. You can prove what we want. Okay, so once you have this properly stated, just by cooking the numbers, you can prove that if instead of K to the C here, you put this and you cook the numbers, you can prove that we can obtain an approximation algorithm with this ratio. And in fact, it works for this choice of epsilon prime. Okay. You can take epsilon prime to be this number, and we can prove what we want. So the proof, maybe this also is not, the full details are not in the archive yet, so we just wait a couple of weeks if you want to take a look at it, but it takes like 2 or 2.5 pages. So it's really nothing difficult, and it doesn't use any complicated technology. It's just calculation with inequalities using really standard techniques of approximation. Okay, so in the last 10 minutes or less, let me show you the ideas we use to obtain subquadratic kernels on particular graph classes. In particular, I will just focus on the case of the bull, which is quite illustrative for the techniques that we use. So this is the nice bull in the picture. And let me define the Erdos-Eisner property. So we say that the graph H satisfies the Erdos-Eisner property if there is a constant delta depending on H, such that if I take a graph G that excludes H as an induced subgraph and has n vertices, then it contains a very large clique or a very large independent set. How large? Of size n to this delta. Okay. So the Erdos-Eisner property says that if I exclude this graph as a subgraph, I obtain a class of graph that has very large, what is called homogeneous, that are either cliques or independent sets of polynomial size in the size of the graph. So the conjecture that you may know is that every graph H satisfies the Erdos-Eisner property, and this conjecture is wide open and is only known for very particular cases, in particular for graphs of at most 4 vertices, the bull in particular, complete graphs, and several other examples. So there's a very nice survey by Chudnovsky on this topic. Unfortunately for us, for all the cases, for all the graphs H that are known to satisfy this property, such a large clique or independent set can in fact be found in polynomial time. Okay? Because if we want to apply this in kernelization, we need polynomial time algorithms. So fortunately, in particular for the bull, such a large clique or independent set can be found in polynomial time. Okay, let me state two simple and useful lemmas that we'll use. The first one is that suppose that I have a graph that satisfies the orthogonal property in a constructive way, as I told you before. So that is not a restriction with constant delta, and take an H-free graph. Then what can we do? We can partition the vertex set in polynomial time into a collection of cliques and independent sets, such that its number is sublinear. Okay? So this is also, again, a simple proof, making the calculations, but intuitively, you take your graph and you remove a large clique or independent set, then you remove another one, then you remove another one until you consume your graph. And since the size of every set is polynomial, let's say n to the epsilon, then if you cook the details, then you can prove that the number of sets that you use to partition the whole set is sublinear. So this will be important for us. And another very simple lemma is the following. So suppose you have a graph and you have an independent set on it. Then we claim that there is the minimum vertex cover that contains the open neighborhood of this independent set. So this property is a generalization of the fact that of this simple property that I told you about vertices of high degree. Okay? So this generalizes it. Why? So suppose that S is an independent set. I consider the neighborhood of it, n of S, in which there may be edges. And what we claim is that there is an independent set containing n of there is a minimal vertex cover containing n of S. Why is that? Okay, start from all these sets. Okay, so start with the set that contains the whole graph minus S. This is a vertex cover because the complement is an independent set. And here, just remove vertices greedily until your vertex cover is minimal. Since here, every guy here, by definition, has a neighbor here, and these guys are not in the set, none of these guys will be ever removed when minimalizing this set. So the size of the resulting set will contain this whole set n of S. So its size will be at least the size of n of S. So we'll use it in analysis. Okay. So what's the strategy? Again, assume we're given an instance of this problem and we're interchangeable free. As I told you, we can assume that the maximum degree of G is at most k minus 1. Then we start by finding greedily a minimal vertex cover X of the input graph. Okay? Of course, if the vertex that I find, the set X that I find has size already at least k, I'm done. I answer yes. So I can assume that the set has size at most k minus 1. And let's call S the complement. So S is an independent set. So to obtain a kernel, it just remains to bound S. So the goal will be to bound S by a subquadratic function on K. And it's known that the bool satisfies the orthogonal property with constant 1/4. So I can apply the first lemma. And I partition the graph induced by the minimal vertex cover. Okay, so not S. I partition the graph induced by the minimal vertex cover into a collection of cliques and independent sets, whose number is K to the 1 minus epsilon. So in this case, it's K to the 3/4. Since I can assume that there are no isolated vertices, I can cover S by considering the neighborhoods of all the cliques or independent sets. Okay, so I take the union over all cliques of its neighborhood and the union of all the independent sets of its neighborhood, I'm covering the whole set. So if I want to bound the size of this independent set, it is enough to show that for any clique or any independent set, its neighborhood has linear size. And in this case, I'm done. Why? Because I will have K to the 3 over 4 sets, each having a neighborhood of linear size. So if I multiply these two numbers, this gives me K to the 7 over 4. So I will be done. So let's prove that. This is our goal. For independent set is easy. Why? Because by the previous lemma, by the second lemma, if I have an independent set whose neighborhood has size at least K, I can answer yes. Okay, so I automatically can assume that for every independent set, its neighborhood in the independent set above, in S, has size at most K. So the interesting case is when I take a clique. Okay? So now the setting is I have a clique in my decomposition of the G of X, or my minimal vertex cover, and I want to prove that the neighborhood, the number of guys in the independent set that are neighbors of this clique, has linear size. Okay, what we will do, so here is my clique C, and I will partition its neighborhood in the independent set into two sets, SC1 and SC2, as follows. SC1 is defined as a maximal collection of vertices in the set, such that when I take any two of them, its joint neighborhood does not cover the whole clique. Okay? So again, I have this set here, and I start packing vertices here greedily with the condition that for any two of them, when I make the union of the two neighborhoods in the clique, I don't cover the whole clique. Okay? So at some point, I may be blocked. Then I'm not adding any more vertex, and I just define S to C to be the complement of this set. Okay? And what I claim is that once I have constructed this set, I claim that these vertices can be ordered x1 to xp, let's say, such that for increasing indices, I have the inclusion of neighborhoods. Okay? So I claim that I can order these guys x1 to xp such that if I is smaller than j, then the neighborhood of xi is included in the neighborhood of xj. So I claim that what is shown in the picture here cannot happen. Why is that? Assume it happens. So assume I have two guys here that have, so that x has a neighbor that is not neighbor of y, and also y has a neighbor that is not neighbor of x. By definition of the set S1, there is at least one guy here that is not covered by the neighborhood of x union the neighborhood of y. So since this is a clique, I wouldn't use a bool. So this is where the bool assumption is used. So this cannot happen. So what I have is an inclusion of neighborhoods. So it means that if I take the neighborhood of S1, there is at least one vertex u, but then u is also contained in the neighborhood of x2, and this u is also contained in the neighborhood of x3. But since I can assume that the maximum degree of G is at most k-1, then it means that the number of guys here is at most k-1. So I'm done with this set. It just remains to bound the size of this set. Okay, let's look at it. By definition, these guys cannot be added here. So whenever I try to add one of these guys here, I'm covering the whole clique. Okay, but since here we have seen that we have inclusion of neighborhoods, it means that there is at least one vertex here that is neighbor of each of these guys here. Okay, so this guy here is neighbor of each of them because for each of them I'm covering the whole clique, and here I need to have at least one guy that is not covered by any of these guys here. Okay, and here I use the degree assumption from the other side. Since this guy here needs to have degree at most k-1, then the number of guys here needs to be also at most k-1, and I'm done. I have bounded the neighborhood of every clique. And we use this kind of arguments for other, as I told you, for other graphs that are distinct from the bool. But I think that most of the ideas are already present in this example. So let me conclude a couple of minutes with some questions. So in our opinion, our main result is this one that, I mean, is not, in our opinion, is not the result for MMVC that is important, is this relation that we discovered. And of course, the natural question is, can we drop the lob assumption here? I mean, can we have the same statement without this lob assumption here? This is will be very interesting. Also, it would be nice to have some explicit example of rules that are not lob rules, so that we're indeed convinced that it is a restriction. And well, as I told you, we have a translation of our framework to vertex minimization problems, but still we haven't found any candidate to obtain a labo bound. As I told you, the main drawback of our approach is that we need a very strong inapproximability result. So here the natural candidates may be the min-max version of maximization problems, such as clique or independent set, for instance. In fact, we didn't try it hard yet. Well, our second main result is that we exhibited subgraphic kernels on restricted graph classes. So the natural approach here, if you want to continue, is to apply it to other graphs that we didn't manage to, and that satisfy the ergosize properties, so that's like the C4 of the diamond, for instance. In particular, as far as we know, the complexity MP or MP hard of an MVC on P5 free graphs is open. So it's a nice question to answer. And the last thing is very interesting in our opinion. So these guys prove that if I take a graph M that does not have isolated vertices, then I can always find a maximum minimal vertex cover of size roughly n to the square root. So this immediately implies, I mean, it is another argument to obtain a quadratic kernel, because if the size of my graph is more than k squared, I can answer yes directly. Okay, then suppose that for any of the H-free graphs that we consider, for instance, the bull, this property is true, but slightly stronger. Suppose that there is an epsilon strictly positive, such that any H-free graph contains an NFVC of size at least n to the 1/2 plus epsilon. Then by the same argument I sketched here, this will immediately imply a subquadratic kernel. Okay. So we tried to prove it like for some of the graphs, like maybe what we did is unnecessary. Maybe there's a trivial bound that already says you that without doing anything, you already have a subquadratic kernel. But for instance, the case of triangle-free graphs is interesting because the maximum size of the minimum size of independent dominating sets, this is the dual problem, on triangle-free graphs has been studied in a number of articles, and it turns out to have very nice connections to the Ramsey numbers. So this trying to optimize this bound here for H-free graphs seems a nice combinatorial problem that will have, as I told you, also interesting algorithmic consequences because it will yield a subquadratic kernel. And that's all. Thank you for your attention.
Thank you so much for the talk. I guess we're open for questions now. If anybody has questions, they can just unmute themselves and ask. Or if you would prefer, you can type in the chat.
Yeah, I have it open here.
Okay.
Okay, may I ask one question, please?
Yes, sir.
Hi, thanks for the very nice talk.
Welcome.
I just wanted to ask if the Erdos Heinel property is it polytime computable? Can we check it efficiently?
In fact, it is. I just borrowed it from the literature. I mean, the definition of the Erdos-Eisner property does not require that you must be able to find the clique order independent in polynomial time. It just, fortunately, in the cases in which this has been proved, the proof yields a polytime algorithm that finds the sets. So, to the best of my knowledge, there is no case that is known to satisfy the property for which it is unknown whether this can be found in polynomial time. But it may be the case. It may be the case.
Yeah, very interesting. Thank you. Thanks.
Welcome.
May I ask a question?
Yeah.
Thanks for the talk.
Welcome.
I hope this is not a silly question, but for the
Don't worry.
minimization problem, can we use some similar argument to exclude for vertex cover, like 1.999K vertex kernel?
For instance, in the particular case of vertex cover, no, because as I said, our framework needs a very strong hypothesis is that the problem cannot be approximated within n to the c or n to the r for some r. So it's a very strong inapproximability result. So vertex cover can be too approximated, so we cannot apply the framework to it.
So it doesn't work for the constant approximation ratio.
Yeah, I mean, in case that you don't have a polynomial inapproximability, our framework, at least in it, it just doesn't work. I mean, as I told, this is probably the weakest point of it, that it cannot be applied to problems that are.
I'm sorry, I think we lost your audio for the last sentence.
Yeah, I got the message here.
Okay.
That again, the framework can only be applied to very hard problems from the inapproximability point of view. So vertex cover, we cannot say anything about the constants multiplying the linear kernel. No. We would like to,
I
but
see.
no.
I see. Yeah, if it works, then it sounds.
But there are some techniques. So one of the of the techniques that I listed was used, for instance, to give lower bounds on the sizes of kernels on planar graphs. And but our framework is not able to do that.
If I remember correctly, that is from four-coloring theorem or something like that, right?
It uses the four-color theorem in particular.
Yeah. Thanks for the answer.
Welcome.
Any more questions? Okay, so I'd like to ask one. So what you mentioned about the LOP rules, that we don't know for the case when there would be a difference between a regular rule and a LOP rule, or like basically when you're trying to reach the LOP kernel. So was this a statement you made like in general, or was it problem specific?
I mean, we don't know. It sounds like a very strong claim, but we don't know of any vertex maximization or vertex minimization problem for which, let's say, the published rules to obtain non-trivial kernels for it are not LOP rules. Yeah.
Okay, got it.
Yeah.
Okay, thanks.
So that's why we think that in this result here, I mean, we think that this can be dropped. But then the arguments that I sketched cannot be applied because it relies on the fact that the optimum is large. It crucially relies on the fact that the optimum is large. But it is this connection, especially when we realize that there is these matching numbers for the feedback vertex set. This cannot be changed. I mean, it would be so strange that it's just random, like the 2/3 matches with 3, like this randomly. I mean, I don't think so. So I think that this can be dropped, but new techniques probably need to be used.
Okay, sure. Thanks.
You're welcome.
Okay, any last questions? Yeah.
I have a question for me. Yeah, could I ask you to clarify a bit what you mean by LOP rules because during the talk you gave an example of a non-LOP rule, which was if you have k plus 1 neighbors, keep only k of them.
Yeah.
So that kind of a rule would in general not be a LOP rule. Like if I have a maximization problem and I say keeping only k of these objects is enough to achieve my goal if I want.
Exactly.
But you're still saying that you still kind of count these under the header of LOP rules somehow, or what do you mean?
So sorry, can you repeat the last part?
I'm just saying. So since you gave these examples during the talk, I'm kind of wondering what you mean, but when you ask for natural reduction rules that are not LOP rules, it sounds as if you don't consider these.
Okay, let me put it more concrete. Like send me a paper in which there is a rule that is not a LOP rule. Let's say. In this sense, I mean, like I would like to have an example of a kernel, let's say a reasonable kernel for a problem that is published in a research article, not in an artificial example as I cooked it here, that is not a LOP rule. Like are non-LOP kernels strictly more powerful than LOP kernels? This is what I mean by
so I can't answer off the top of my head if this is exactly what you're looking for, but there is a paper about kernelization for, what is it, deletion 2/3 or something of this order. It's
what do you mean?
It's a paper where I have a polynomial kernel for an inapproximable problem, and the way that you get away with it is this kind of thing where the maximization problem is infeasible because of weight, but as a kernelization, you can still reduce the instance. I mean, if you're curious, I can't dig the reference out of my head right now, and I can't promise it's what you look for, but it might be worth looking at.
Definitely. I mean, it will be really nice. It will be. I don't know if it will be good news or bad news for us, but we think that, of course. I mean, I'm saying it to provocate, let's say, because I mean, there should be some, because it is a very strong claim, right? That all rules are not lob rules. I mean, all kernels are lob kernels, but they will be really happy to find an explicit kernel that is not a lob kernel. So if you have some pointer, I will be very interested. Thank you. If you have some pointer to this. I'm not sure I've answered completely your question, because I think it was in between a question and a remark, but well, if not, we can discuss later.
I kind of take your answer as saying that you're really looking for reduction rules that cannot be turned into lob rules rather than rules that are not already lob rules, because that's kind of...
Yeah. Okay. Yeah. I mean, of course, there will be an intermediate step, right? I mean, one could find a loop that is not a lob rule, but still maybe it can be turned into a lob rule. I mean, and then there will be an even second step will be, okay, here is the rule, and I have no idea how to turn it into a lob rule. I mean, now I think I understood. I mean, you are concerned about that are not lob rules. I mean, what does it mean not to be a lob rule, right? I mean, it's like a meta question.
My original question was just, why do high degree rules, such as the example you gave, not count? That was my... Okay, but maybe we should take this offline at some point.
All right, then. I guess this is a good time to conclude. So yeah, thank you so much for the talk. It was great to have you. And we conclude our session for today here. And thanks to the speaker for the talk, and thanks to the audience for being around. So see you all next week. Thank you. Bye.